The alternative hypotheses would be not equal to, greater than, less than. Not equal to number, so the null hypothesis would be this, or this. The alternatives are not equal to the number, greater than the number, less than the number. You can do the rest of these, you know what to do, right? All right, so the realistic situation, this is not known. Okay, so I will substitute S is used in place of sigma, therefore we use T distributions. Why do we use T? Because the outer tails are a little higher and they create a safer calculation for highly variable samples. Yes?
Well, how come the standard deviation isn't known in a realistic situation?
Well, you're taking sample values and you're trying to predict the population. Well, population standard deviation you wouldn't know because you're trying to predict it from a sample.
Oh,
Yeah, does that make sense?
yeah.
Okay. It seems like, because we used it in chapter 9 like you knew it, that, hey, you should have it. In reality, it doesn't work like that. Okay, so we did it that way in chapter 9 so that you can practice doing z-score calculations, and it looks like what you're going to do anyway. Okay, except we now change it up to use T. So, requirements for any test. So requirements for significance test or a confidence interval are, it comes from a simple random sample, or if it's a two-sample thing, both are simple random samples. If it is so for one it's a simple random sample, it needs to be the differences are, or act like a simple random sample. I guess they're still, so for matched pairs and two-sample test, every sample has to be a simple random sample. For the is it normal, of course, n greater than 30, central limit theorem works. T also works when n is between 15 and 30 for moderate skew is okay. Okay? When sample sizes are smaller than 15, T okay if mild skew. Not much. So it needs to be approximately normal. Now how can you tell? You can plot the data, it can tell you the population is normal, okay? Or you gotta use central limit there. And the other thing you need to do is S over square root of n okay? Yeah, it will be if 10 times the sample size is smaller than the population. So whenever I do a confidence interval, I have 5 steps. Interested in, I need to write them out. Interested in, test I'm going to do a 1 sample, I'm doing a matched pairs, I'm doing a 2 sample confidence interval for a mean using T procedure. Requirements for the test, these. Calculations would be for a confidence interval, x bar plus or minus T star sigma square root of n. X bar are the differences, plus or minus T star S of the differences over square root of n. X bar 1 minus X bar 2 plus and minus T star S1 squared N1 plus S2 squared N2. And this is from a smaller sample. If the samples aren't the same size, if n is not equal, you pick the higher value there. You know, those are confidence intervals. Yeah? Then if I did significance tests, I would do t critical value is x bar minus mean over s square roots of n. For a matched pairs design, it would be t equals this and the differences minus the mean, or the believed amount of differences, which is going to be 0. Right? We believe there's no difference in our null hypothesis, right? And then we're going to do S of the differences. This might be your list 3 divided by square root of how many there were. And if I was doing a 2-sample test, it would be x bar 1 minus x bar 2 all over. We don't pool, so I'm just going to do S1 squared over N1, S2 squared over N2. Chapter 11. Chapter 12. Okay, so T is for me. Then I would do chapter 12. Z is for proportion. Okay, and the null hypotheses go pretty much the same, but it's now going to be P equals to some decimal number. Null hypothesis might be P of the differences. We hardly do matched pairs for proportions, but you guess you could. I'm going to do P1 equals to P2, and so your alternatives are not equal to, greater than, less than, not equal to, greater than, less than. Everybody happy with that? Yeah? If I'm doing a confidence interval, it's going to end up being P hat plus or minus Z star P1 minus P over N. If I don't know this number, I use P hat. If I'm doing a 2-sample or difference in 2 proportions, it might be P1 minus P2 plus or minus Z star. And I don't pool for confidence intervals, so P1 1 minus P1 over N1, I guess it might be P hat plus P2 1 minus P2 all the hats over N2. So for a confidence interval, looks like that. For a significance test, I would do, for these, that would be a significance test. I would end up with P hat minus P over P hat 1 minus P hat over N, or depending on whether I knew what it was. Okay, so sometimes P hat goes here sometimes. For a 2-sample proportion test, I would end up doing P hat 1 minus P hat 2, all of it over the pooled 1 minus 1P, 1 over N1, 1 over N2, square root here, where this is the pooled proportion, which is x1 plus x2 over N. Come on, man. N1 plus N2. And these end up being, by the way, a z-score. This ends up being a z-score. And we interpret the p-values like we always do. For proportions, simple random sample. Normal is found by doing, for a 1-sample, NP greater than 10 and 1 minus P greater than 10. If it's a 2-sample, it would be N1 P1 greater than or equal to 5, N1 times 1 minus P1 greater than or equal to 5, N2 P2 greater than or equal to 5, N2 1 minus P2 greater than or equal to 5, if it's a 2-sample test. and it's still 10n smaller than population, allows us to use p times 1 minus p over n, or all of its morphs. To keep the margin of error a certain size, we just pick that part of the formula and manipulate it. Right. That's the bulk of it. If you want to, I got a little out of whack over here, kind of going in circles, but it's all on there. Power of a test would be the same. Type 1 and type 2 errors are the same as before. Anybody think of anything I've left out? Did I leave anything out, Mo? I feel like I could do the test, but I don't count. Should I stand in front of it and smile while you guys take pictures of it? Yeah.